Good morning, everyone. Welcome back to class. Today we're going to be talking about linked lists. This is sort of motivated by yesterday's discussion on tables. So we'll do a little review of that first. Remember that the table is an ADT that stores data by keys, rather than like going through items in a specific order or getting an item directly. Each item is associated with some way to find it. A common example that we're going to probably talk or bring up over and over is looking up students by student numbers. The students with information like grade, name, email address, attendance record if you take that, would be the entry, and the key would be the student number. There are a whole bunch of things that a table can do, but we're going to focus on just three. Insert puts a new record into the table. Search takes a key and returns the item with that key, or some sort of error value if an item with that key doesn't exist. And delete, which takes a key and removes the item associated with that key from the list. Again, returning some sort of error value if the deletion isn't possible. Notice how those descriptions have nothing to do with how you're actually implementing this thing. The big two data structures are arrays and linked lists, and I said nothing about array indexing or pointers or any of that stuff. We talked about implementing the table using an array a bit in the last class. And this class, we're going to talk all about linked lists. This should hopefully be a review from earlier comp sci courses. I don't know exactly how the curriculum works, and every student's path is slightly different. But this lecture will be a lot more about implementation details than anything else. And I hope it continues to be a bit of a relief from the asymptotic notation stuff from last week. The important part about a linked list is that space for each entry is allocated only when needed, as opposed to an array where you allocate space for a fixed number of items when you allocate the array. Each entry contains the thing that it's storing and a pointer to the next entry. Like if I wanted to store students, it's like saying that each entry includes information on a student and the name or student number of whoever's sitting beside them right now. There are several variations of a linked list, several implementation details or implementation decisions you'll have to consider when making a linked list. The first big one to consider is whether the linked list or whether the item should be in sorted order or in unsorted order. In our student example, that means whether the student number should be always increasing or always decreasing, or in whatever order you want, just like chronological order of registration or something. I guess that would be the natural order. So we're trying to make a table. Would we choose sorted or unsorted? There's no objectively correct answer to this, but the lecture goes over some advantages and disadvantages of them. I think my choice would be unsorted because it makes the insert operation really easy, and then the negative effects it has on search and delete aren't really that bad. To elaborate, if you're inserting an item into a unsorted linked list, you could just throw it at the beginning. You don't really have to think about any of it. Contrast to a sorted linked list, where you would have to find where in the list the new item would best fit based on its key and put it in the appropriate location. And I think this slide contains, finally, our first example of asymptotic notation being used in a more real-world context. It says here, time complexity O of 1. Notice how we didn't implement the insert operation. We didn't count steps or prove from the definition or anything. We just gave a quick informal explanation that the stuff that the insert operation doesn't depend on the number of items that are already in the linked list. So it must take constant time. That's big O of 1. I don't think necessarily that all the stuff you've done on asymptotic notation is a waste of time per se, because it's good to know exactly what you're talking about when referencing these mathematical concepts. But when you're working a real programming job in the real world, this is roughly how they use asymptotic notation, as a quick way of comparing speed of variables based on an informal observation of what it does. While I still think that the unsorted linked list is better for this scenario, there are some benefits to maintaining a sorted one. So in arrays, sorting the data can get you a massive advantage because it lets you use the binary search algorithm that hopefully you learned about in first year. For the sake of access to binary search, it's a good idea to sort your data when it's used in an array. But with a linked list, you can't binary search because there's no random access. If you're telling your code to access item with key 2, it just doesn't have the ability to go straight to key 2. You'll learn a bit more about how that works in Comp 2160. Instead, it has to start from the top. Check this. Is this 2? No. Go to the next. Is this 2? No. Go to the next. Is this 2? Yeah. That's kind of slow. A lot worse than being able to split the list in half. Is this 2? No. Split the list in half again. Is this 2? Yeah. The speed advantage gets better and better the larger the list is, because binary search is big O of log n. Anyway, the speed advantage that you get for searching in a sorted linked list isn't as good as in a sorted array, but you still might get a bit of an advantage. Say student numbers are allocated in linear order. The later you register, the larger your student number is. So my student number will be a lot smaller than all of yours because I'm old, I've been here longer. So maybe you're sorting student numbers in your linked list such that the largest ones are first, and in a more practical sense, you tend to search for newer students more often. Newer students are more likely to be registered in classes currently as opposed to student number 000000001 who has been graduated for 50 years and is probably dead. You won't Or you can imagine a scenario where if you sort the keys in some order, you'll search for a certain side of the sorted list, in this case, students with larger student numbers, a lot more often. So if you sort those, then you might find that search operations will exit sooner because they'll just be more likely to get those larger student numbers first. Again, if the student numbers are sorted in descending order, largest first. This is actually a neat example of the weaknesses of asymptotic notation. Whether the student numbers are sorted completely randomly and a given student could be anywhere, or if they're sorted in descending order and newer students are more likely to be at the start of the list, those are both considered linear time, big O of n, because the time that it takes to search scales linearly with the number of items in the list. The cost function of sorting a list with n items would look something like 3n plus 2. They have the same asymptotic time complexity, but the sorted case will be a bit faster on average. So that means that even if two algorithms have the same asymptotic time complexity, in this case they're both O of n, there's still room for more subtle speed differences. Moving on, we can suppose we need to enforce uniqueness, so each key can appear no more than once. I think that makes sense for a school example. If you had two students with the same student number, that would be awfully confusing. Then insert would need to search the entire list to check for duplicates before adding the new entry. In this case, insert will have to do a search anyway, and if it's unsorted and you're adding a new unique entry, insert would have to traverse the entire list in order to verify that its key doesn't exist. So in this case, the sorted list would perform way faster because, say you're registering an entirely new student, has a new student number, it would only have to check a few entries at the start to verify that it's a new student number, as opposed to an unsorted list where it would have to search through every student ever registered. Probably a really bad implementation of this idea, but it would have to do a lot more to do that insertion. I'm kind of convincing myself that the sorted linked list is better, actually. In any case, we said before that an unsorted linked list would be better because of constant time inserts. But if we're enforcing uniqueness, then suddenly a sorted linked list becomes better because of these more subtle differences in certain searches exiting sooner on average. Here's some pseudocode for linked lists. I know you're hopefully started assignment 2 now and are knee-deep into that, but this may or may not be a bit of a hint for assignment 3. It's probably going to have something to do with linked lists. Anywho, I'm going to sort of stall for time and talk a lot on this slide, but while I'm talking, try to pinpoint on your own some things that I forgot to do when writing this pseudocode. Because even though it sort of checks all the basic boxes of how linked lists are supposed to work, there are a lot, or at least 3, ways that you can crash this. So you have previous and current node. Oh yeah, sorry, it's for an insert method, not the linked list itself. The stuff about me getting a bunch of things wrong with this code still stands though. Anyway, you got two references to nodes. To search for a node, you loop for as long as the current node's data is less than the new data. This linked list is probably sorted. So once that condition is false, then we'll have the place where the new node should come in. So the current node will be the one that the new node should link to. So while that search condition is true, that is while the new node to add isn't in its right place yet, we just sort of shift the nodes backwards. Previous node becomes current node, and current node becomes its own next node, the node that it was pointing to. Then, when we're done, we create a node that contains the data we wanted to insert and the node that it's pointing to. And then we take the previous node's link and we make it point to new node. So what we're doing is creating the new node and then making it point to current node.link, and then replacing the current node's pointer to one that points to new. So I think I've spent enough time on this slide. Not going to ask anyone to put their hands up because I know that's real scary for you, and it's kind of awkward for me when I go like, hey, any questions? Or any answers to the question? And there's silence. So let's just move on. However, of course, if anyone wants to put their hand up for any reason in the middle of me talking, feel free to do so. I'm just not forcing you. There are three special cases that I failed to address. Those are if the new node is added at the end of the list, the new node is added at the beginning of the list, and the new node is being added to an empty list. So we're basically going to need to patch this up with a bunch of null pointer checks. You could see in the pseudocode that we basically never check for null, and more insidiously, we never, or we always assume that cur node is not null because we access its data property. And also, we keep assuming that the current node's link is non-null. So, like, if the node is meant to be put at the end of the list, then cur node will be null at the end of the loop, and then I think prev node will be null, and then that'll break. And of course, if it's empty, if the linked list is empty, then we run into the same problem as adding it to the beginning. This will crap out. So here's an attempt at making this better. It's closer to the kind of stuff that you should hand in on assignments and make in the real world. But there's still some improvements we could make. it's like the old code, but we keep checking for null. While the old condition is true and current node is not null. And then at the end, when we insert, we make sure that previous node is not null. Making these checks will prevent the null reference exceptions that could occur when using the old one. But it's kind of ugly. This is kind of another general lesson for coding. There will always be special cases, edge cases, in how your data structures work. And one way to deal with them is to make something that looks like this, attempt to use it, watch it break over and over again, and then keep adding, like, if the thingy is null, else, blah, blah, blah. Just keep putting Band-Aids on it. But through better design of your code, you can actually make it so the erroneous cases aren't even possible. And then you'll end up with cleaner and more resilient code. So here's something that we could do to fix the linked list. We could add a thing called a dummy node that marks the start or end of the linked list. It doesn't contain any data, but it exists for the sake of making it so there's always something non-null at the beginning and end of the list, even if the list is empty. Whether or not to include these will be implementation specific. I don't know, you might have a situation where you know for sure that items will never be added to the start or the end of the list, only the middle. And then this stuff would be unnecessary. But in most cases, this is a useful thing to consider. So assuming you're adding dummy nodes to both the start and end of the list, you call the nodes the header and the trailer, respectively. So the header's at the start, the trailer's at the end. The trailer trails. It's memorable. Did you know that movie trailers were called that because they used to be played at the end of the movie? It's weird. Maybe they should be called headers now. Anyway, they're created by the constructor. So this is what an empty list looks like. Just a reference to the header, and the header points to the trailer. This, it turns out, makes all those null checks unnecessary. It makes those cases where the variables could be null impossible, which is really nice. So top is never null because it always points to the header. Every node has a predecessor. If it naturally has a predecessor, then it's exactly what you'd expect. But if it's at the start of the list, it's the header. And then also, every node has a successor or a link. Similar to before, if it naturally has a link, like it's succeeded by something that's actually in the list, then the successor is exactly what you'd expect. But if it's at the end of the list, then its successor is the trailer. Because of that, you'll no longer have to check for null. But you might be thinking, we might have to still check for whether the node is a dummy node or not. But you could do that pretty seamlessly too. You do that in a way that's sort of specific to whatever application you're designing software for. Application as in use case, not application as an app, although I guess that still applies. So you'll do this differently based on what you're actually writing code for. But you'll want to make the data in a dummy node distinguishable from real data. And that is accomplished most of the time using extreme values, things that'll never show up in your actual data. So in our student ID number example, student numbers can never be less than 0. And ideally, they will never be larger than 1 with 7 zeros after it. This might not be future-proof for like the far future, but whatever. You could make it so the largest extreme value is 1 times 10 to the power of 8, 1 with 8 zeros after it. A more general solution you could use, which I prefer, if the data are integers but we don't know the range, use the constants built into your programming language and use the minimum value and the maximum value. There'll be something like positive and negative 2 billion, which should work for most scenarios. These are far from the only ways to store extreme values. If your application has integers that could feasibly be the minimum value and the maximum value, you might want to use a larger type, like long instead of an int, and then store larger values through that. You could use pointers to integers instead, and then your extreme values will be null pointers. I thought of one that's way more practical. If you're using floats, you could store those as, you can use negative infinity and positive infinity. There are lots of different ways to do this. Here's another variant of the linked list. Instead of using a dummy node, or instead of using dummy nodes, several, you could make the link the last node just point back to the first node. It's circular. This makes it so no node has no successor. No node has link equals null. But top could be null. Like there can still be an empty list. So we can add one dummy node to the linked list. So this is another way of achieving the same ideal as the previous example. You have no reason to ever check for null because your pointers will never be null. Whether you go with a circular linked list or something with dummy nodes will depend on your implementation, or will depend on your application requirements. Some ramblings that might help are that the circular linked list is a bit more elegant, I think, than the dummy nodes. You don't have as much stuff that's only there to prevent null checks, don't have as much useless data. And it may be helpful to only need a might be useful to only need a header node if your data has a minimum but no maximum. So like student numbers can never be negative, but they could theoretically go on forever, infinitely large. This would help. But a disadvantage to circular linked lists is that searches can potentially go on forever. This is partially, hopefully, mitigated by the dummy node. But you could imagine a unsorted circular linked list where you have to find an item and it goes like, is this the data I want? No. Is this it? 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 Forever and ever and ever. So when you're choosing the variation of linked list to use, you would have to consider whether that is a thing that could happen, or if all searches are guaranteed to have the search target in the list somewhere. Lots and lots of implementation decisions. And of course, assignment 2 is the big thing right now. You're still immersed in asymptotic notation when you're working on this course outside of lectures, but you'll definitely have to make decisions like these in the future, in assignments and all the time in the real world. This is what an empty circular linked list with a dummy node looks like. Wahoo! An empty circular linked list with no dummy node would basically be nothing, no links, just top is null. And then those ugly null checks from the example earlier would be used to add the first node to an empty list and then make it point to itself. Here's another one. Is a doubly linked list. Instead of each node just pointing to the one after it, it also points to the one before it. So you can see here, each node has a back and a forward pointer. And then you could also reuse what we just talked about with the doubly linked structure. You can have stuff like, we can reuse the stuff we already learned, with the doubly linked structure. We could have it circular, can incorporate a dummy node. And then that's what it would look like while it's empty. I'm going to try and think of an example of why you would want a doubly linked list. I don't know, maybe you're sorting or logging events that have happened, like, I don't know, you're a server administrator or something. I don't know why you're not using a more fancy database to store records, but I don't know. When you're troubleshooting something that's happened on a network, individual events are important, but you also want to find things that have happened right before and right after. Again, that's a really contrived example because system administrators wouldn't just directly use a linked list to store system logs. They'd use much more intensive, complicated programs, but I'm not wrong. When you're troubleshooting stuff, you would want to look at individual events as well as events that have happened before or after it. So now it's time to think a bit more and use some more asymptotic notation stuff. Using asymptotic notation, in this case, big O, You want to think about the time complexities of insert, search, and delete in terms of n. More interestingly, is there any combination of properties you can choose that will cause your answers to be different, or are they all the same? I guess I kind of spoiled that earlier in the lecture. The answer is obviously yes. But how does that happen? I want to mention as well that even though all of the 5 pieces of asymptotic notation you learned are used in general, big O is by far the most common because it gives you a worst case for the resources that your program or algorithm might use. So say, hypothetically, your linked list is set up such that insert takes big O of n operations. That means that it will never do worse than linear time. So like the time the algorithm takes to execute grows linearly with the number of items in the list. But it will never do worse. If you have if you have 5 items in the list, it'll take less than 25, something like that. But it could do better. You could end up with like n over 2 operations, 5 steps taken for 10 items, something like that. But O of n means that it takes at most n-ish operations. A function that's in big O of n. You know this. So yeah, big O is by far the most used in the real world. Others are used too sometimes. I think big theta is a close second because it's more precise than big O. Big theta of n means that the cost function must be linear time or linear growth. And for the other question, it's to describe the memory required to store the linked list in terms of n. You should definitely think about these on your own, either while I'm talking or after class, although I will go over the solutions once I'm done talking about the questions. I think question B is another interesting example of a general concept, and it's that using asymptotic notation to measure resource use, time isn't the only thing we're measuring. Time is the thing that's most often measured because we care a lot about how long our code takes to run. But another very relevant measure of complexity is space complexity. How much RAM does your program take? So time is the thing most often measured, space would be second, and then there are a whole bunch of niche measures of complexity. Like if you're programming something that uses network communication, you might want to use asymptotic notation to describe the number of network accesses you need. Can I think of any other examples? Memory accesses is another. Not necessarily the amount of memory taken, but how often you need to read from memory. You'll learn in systems courses that accessing memory is actually super slow relatively to your processor actually doing math on its own. So sometimes you might want to measure memory accesses in addition to all other primitive operations for time or the amount of memory you're taking up. So let's end this off by looking at the answers. Regardless of whether you order or if you sort the list or not, search is always linear time. That's kind of the big weakness of linear lists, or of linked lists, where the big advantage is the fact that you don't have to allocate space ahead of time. The only search algorithm you could do on a linked list is linear search. It's going to take O of n operations every time. Since delete has to find the entry to be deleted first, like it has to search for the thing it's deleting before deleting it, it's also O of n. Sort of like how on assignment 1, the standard deviation function called the mean function, so the standard deviation function could never be less complex than the mean function. Insert is where it gets interesting and calls back to what I talked about earlier. It's O of n if we keep the entries in order. So like it'll take a constant number of operations per entry in the list, roughly, asymptotically. But if it's unordered and you always insert the new entry at the start, then you get constant time. You just put it at the start of the list and make it point to the former first element, regardless of how many items are in the list. That actually opens up the possibility of a faster delete algorithm. I said that you need to search the list for the thing you're deleting before you delete it. But if you know that you're always going to delete the first or last item in the list, that's something that comes up when you're writing stacks and queues. You could make an operation that's like delete first or delete last, and that'll be constant time. Again, comprising an advantage over an array. That's cool. And finally, every variant of a linked list requires big O of n memory space. It's basically impossible to get a data structure taking space less than O of n, because like you have n items and you have to store them all using some number of bits. I suppose maybe if you're doing compression, you could technically say you're using less than 1 bit per item, because you're like compressing it and abandoning some part of the data, but like that's weird. If you're using dummy nodes, you might need 1 or 2 extra nodes worth of space, but that doesn't change the or the space complexity. You've seen a few examples already with things like n plus 2 is in big O of n, because they both grow linearly. Actually, you could think of that like calculus. Both n and n plus 2 have a derivative of 1. They both have the same rate of change. Might be a useful way to think about it. The space required is still big O of n. The use of doubly linked lists increases the space complexity in a different way. Instead of adding a constant amount of overhead, an amount of overhead that doesn't change based on how many items are in the list, it introduces some overhead for each item in the list because of all the extra pointers. So if a regular linked list took n space, then a doubly linked list might take, 3n space. The derivatives of those are both constants. They're both in big O of n. The asymptotic time complexity doesn't change. Yeah?
So if in some test or exam question we write O2n instead of O1, will it be a mistake?
It's like mathematically not technically wrong, but it's really not how you're supposed to write it. It's like making a spelling mistake in an essay. Since 2n is in O of n and n is in O of 2n, O of n and O of 2n are the same thing. They're the same set. They equal each other. So, yeah, they're mathematically the same, but we tend to just write the simplest possible form of it because that just looks nicer. Do we need to read this? I guess it's kind of important. You just found your first example of a data structure. In the future, I would say next week, but it's only Wednesday, and I guess I'll have to start preparing a bit of next week's stuff early. Next week, i.e. Friday, we're going to look at more ADTs and more possible implementations of those. But the many variations of linked lists we found will be useful for implementing them. Linked lists allocate space only as needed, as opposed to arrays which allocate space all at once. It searches in linear time, which might make it worse than arrays which can do binary search in log n time. But there are several cases where you could use constant time operations on it, which can probably give linked lists advantages over arrays in specific scenarios. That's all for today. Good luck on tomorrow's quiz, and let me know if you have any questions.